Hi guys, welcome back. So normally I'd like to show you what I did over the spring break, and I like to go down to Stratford, to the ranch, but unfortunately I'm not able to do that because no one's really traveling these days. So instead I'm going to show you what I did last spring break. So this is me and a cow. They have about 50 head of cattle down at the ranch, my uncle and my grandmother's place down there. And so last spring break was pretty cool. I actually got to help deliver a baby calf. So proof of it is right there. So you can see it's kind of gross, but you know, the miracle of life. It's awesome at the same time. So its mom is a heifer. So it was her first calf. And so she was having complications. And if you see up here, she actually stuck her head in between the gate and the side panel trying to get out. So she put herself in head gate, which is a miracle. Otherwise, we couldn't safely help her deliver her calf. So that was amazing. And once the water breaks, you got about an hour to be able to deliver the calf before the chances of it surviving go down. So not Debbie Down or anything. The calf did survive. So this is a picture that my uncle sent a week later. So healthy, and you can see he's already gained a lot of weight. So and that was last year, so now he's doing even better, and he's fine. So pretty cool. I got to help deliver a baby calf. When babies are born, they smack the back of them so that they cry, and it clears out their lungs of the amniotic fluid. Then they take their first breath, which is pretty cool. Anyway, similar thing with calves, but you tickle their noses with the straws, what we did, and that causes them to sneeze, which is like a puppy sneezing. It's adorable, even though they're not that cute. When they first come out, they're all like deflated and flat and everything, but whatever. You get the idea. So pretty cool stuff. All right, so we're going to be moving into our last unit, which is inference with means. So we just finished up inference with proportions. A lot of the formulas are very, very similar. The concepts are very similar. This is the last unit that we have to go through for the AP test, and we've got 5 weeks to do it. So this should be pretty smooth. I don't see any issues going forward from that. So sampling distribution models, that's what we've been talking about. So this is inferential statistics. And the sampling distribution model is the distribution of all the samples that we would expect centered on that sample proportion. So let's say that we were flipping a coin. Well, on average, we'd expect the proportion of the coins to be about 50%, right? Because it would be, if it's a fair coin, it would be 50%. But not every sample is going to give you 50% heads, 50% tails, and that just depends on your sample size, right? So this is a sampling distribution model. Let's say that we have 100. We flip 100 coins. We'll do that example on the next page, so just wait for that. But basically, we have our sample proportion, which is 50 here, and then we want to know, is our sample, is it statistically significant or not with our hypothesis test, right? So basically, we look at our sample, like the Los Redes reefs, which had like 56%, 56% of them, of the Los Redes reefs, were infected. From that, we want to know what's our confidence interval, right? We know that can't be the actual true value, so we want to know, okay, so we're 95% confident. Where's the true proportion going to lie between? So that would be creating a confidence interval. And then last thing we did was hypothesis testing. So we would always start with our null hypothesis. So we're going to assume that it's a fair coin, which is 50-50. And then until we have a proportion that's in the top 1%, 5%, or 10%, if that was true, assuming the null hypothesis was 50%, until we have a rare sample, rare enough that would be considered statistically significant, we won't be able to reject the null hypothesis to claim that it's a fair coin, for example. So just a quick review of the things that we talked about in our last unit: sampling distribution models, confidence intervals, and hypothesis testing. Those are the 3 things we're going to be talking about. But now, instead of talking about it with proportions, we're going to be talking about it with means. So here's our sampling distribution model for a fair coin. So our P and our Q are 50%. So we're assuming the probability of success and failure is 50%. We're going to sample 100 coin tosses. We're not actually going to do that, just talking about it in theory, which is nice because we can do that with stats. So the sampling distribution model standard deviation is going to be about 5%. So centered at 50% with plus 5% each standard deviation that would go over. So that would be 50, 55, 60, 65, and then going down the other way as well. All right, but let's say that we did sample 100 coins, we flipped 100 coins, and that we got 52% heads. So 52 out of 100 of our coins were heads. So we would assume that based on that, so I should have locked that horizontal. Let me do that real quick. Let's see. There we go. Sometimes that keystroke doesn't like to work. Okay, so we would assume that the proportion is not actually 50%, but that would be 52% based on our sample. So from that, we would create a confidence interval. So what do we think the true proportion of heads would be with this coin if it was not actually a fair coin or something? So from that, we create a confidence interval. Now notice how this is not the same as a sampling distribution model. Sampling distribution model is based off our null hypothesis and whatever the true proportion is, right? But our confidence interval is based off of our actual sample itself, which in this case was 52%. So we go about 5% in both directions as well. If you notice, the formula is slightly different. It says standard deviation. Now we have the standard error, right? So the reason it's standard error is because this is calculated based off of our p hat and our q hat, which we know is not the true proportion, or not the true proportion and p and q, right? So instead, we call it the standard error because there's going to be error in our sampling, right? Each sample is going to vary from sample to sample. So notice our standard deviation or standard error here is slightly smaller than the actual 5% that we would expect if the true proportion was 50%. So that's not, in the long run, that's not going to change much, but that's why it's standard error. So to create a confidence interval from here, let me switch to the pen real quick. If it'll let me. There we go. Computer's a little slow. All right, so if we go 2 standard deviations out, or about 1.96 standard deviation out in both directions, then we could create a confidence interval that would be, I think that was 95% confident. So we'd be 95% confident that the true proportion lies somewhere between 2 or 1.96 standard deviations in both directions. So it's the same stuff we've been doing. So there's that exact stat that I was trying to show. So the confidence interval here is going to be equal to our sample proportion plus or minus some critical value times our standard error. Now our critical values come from the inverse normal model, which is just the normal distribution we're finding the area underneath the curve. Okay, so for 90% confidence, this is our critical value. That's how many standard deviations we have to go out. 95% is 1.96, and then 99% is 2.58. So to create a 95% confidence interval, it's going to be centered out of proportion, which this is a different example or whatever, and we go 1.96 of these standard deviations or standard errors over in both directions. All right, so all stuff that you guys have seen before. All right, this slide, a picture is worth 1,000 words. I'll try to explain this one in less than 1,000 words, but there's a lot going on here. In fact, this is, I've been excited to show you this for a long time, but this is basically showing you the whole process of what's going on with sampling distribution models and where they come from. So we're going to talk about this with proportions first, then I'll shift to means in just a moment. So let's say that we have our fair coin, the true proportion is 50-50, right? So this is the population's distribution. We would expect 50% heads and 50% tails. So if we did infinitely many samples, eventually it would settle to the empirical probability of 50% heads. That's the whole point here. So from that sample population, the population distribution, we can draw a bunch of samples, and these are distributions of those samples. So some samples are going to have more heads. In each sample is going to vary from sample to sample. Another sample, this one might have more tails than heads, and then this one had even more heads than tails than the last one. Making sure this is all working. Okay, yeah, I just have to hover closer. All right, so that's our sample distributions. Now, if we take the proportions from each sample distribution and we put those all together, so all those proportions are coming together. I'm using an 8-year-old laptop, so I'm building one this evening, so hopefully we won't have these issues. And it takes like 2 hours to render all these videos. It's very annoying. I've never asked this laptop to do all this stuff before. So if we put all those sample proportions together, that'll give us our sampling distributions. So these are the sampling distributions of all of those proportions from the samples. Now, if we increase the sample size, or as we increase the sample size, and we take infinitely many of those samples, then these will both, this is the central limit theorem, the sampling distribution model will approximate that sampling distribution very well, and regardless of what the shape of the original population was, which is really nice. With proportions, the sampling distribution model standard deviation is the square root of p times q divided by n. So all good stuff here. So let's look at what happens with means. So this is an example straight from the book. So if we take one dice and we roll the dice 10,000 times, this is the distribution of the population. So when the sample size is just 1, that's the population. So we would expect this to be unimodal, right? So we would expect all of these dice to show all the same amount of times, right? So we would expect the same amount of ones, rolling a 1 as we do 2s and 3s, 4s, and 5s, and 6. So we expect this to be unimodal going across the top, but it's not actually unimodal. And that's just because we have variation in samples. So from sample to sample, I guess I should change that one. Yeah, so we would expect that to be unimodal and flat across the top, but it's not that way because there's variation in samples. Even if we have a sample size large, like a sample size of 10,000, it's still not going to be perfect, but that's okay. So what happens when instead of just the population, we take the average of 2 samples, or 2 dice average? So now our sample size is 2. We're going to roll 2 dice and we're going to find the average of those 2 dice. Well, as we would expect, that would be centered at 3.5. And we've looked at this triangular distribution many times before, and it even has its own name. It's called the triangular distribution. So on this one, it would be really rare for us to have an average of the dice of 2 dice to be 1, right? The only way that would happen is if we rolled snake eyes, 1 and 1, right? Same thing on the other side with an average of 6. That would only happen if we rolled 2 6s. But most of them are going to have an average of 3.5, right? Rolling a sum of a 7 is the most common, right? We looked at that when we looked at the game of craps. So that's why that's going to be our mode, and we have this nice triangular distribution. Now, is this distribution, does it look like a bell curve? No, but it looks a lot more than this one did. So even though our population was unimodal, our sampling distribution model, as the sample size increases, is going to become more nearly normal, which is pretty cool. So that was an average of 2. Now let's look at an average of 3 dice. So again, the center, the mean here is about 3.5. We're still going to expect an average dice of roll of about 3.5. Having 3 1s, rolling 3 1s at a time, that's going to be really rare, right? So 1 over 6 to the 3rd power. Same thing with having all 6 of these, all 3 of the dice rolling a 6. So again, if we notice, this is going to be more nearly normal than the last one. It looks even more than the triangular distribution. So what about if we roll 5 dice and we take their averages? Well, as you can see, this is very close to a normal model. So as we increase the sample size, regardless of what the population looked like even when it was unimodal, the sampling distribution model will become more nearly normal, which is the central limit theorem. It's the most important theorem of all statistics. It's like the fundamental theorem of statistics, in other words, is what it's called. The central limit theorem, the central part's not telling you, it means it's the central theme of all statistics, the central formula, in other words. So here's another animation of the whole process, but this is showing what we just did. So we started out with our population distribution, which is roughly unimodal, right? This is when we have a sample size of 1. This is such a good slide. Then we have our sample distributions. So if we take different sample sizes of 5, so we roll 5 dice. This one had 2 1s, a 2, a 4, and a 6, right? We could have had a 1, a 4, 2 5s, and a 6, right? And lots of different possible sample combinations. So these are our sample distributions, and we take infinitely many of those. So as we take infinitely many of those, we take each one of their averages. So the average of all these dice, the average of all these dice, and of all these dice for samples, and we put them all together. When we do that, we end up with this sampling distribution, the sampling distributions, which, as we notice,
looks roughly unimodal and symmetric and nearly normal, right? So that's where the sampling distribution model comes in. So the only question, oops, I don't know what I did there, that we have is, what is the standard deviation for that? Well, when it was a proportion, it was a square root of p times q divided by n. But now that we're dealing with means, because we're taking the average, like average height, instead of looking at proportions, our sampling distribution model standard error is going to be, or standard deviation, I suppose I should say, in this case, because this is based off of, like, if we do the actual parameters and we're not just using the statistics, is going to be the standard deviation of the actual sample itself, which would come from the population, divided by the square root of n. So it's still decreasing by the square root of n, which is where we get that whole diminishing returns. So I deleted that slide, but now I understand why I should have shown it. So the square root, so y is equal to 1 over the square root of n is going to look something along the lines of that. I know the handwriting is absolutely atrocious, but we're working on that. All right, so anyway, as we increase the sample size, the standard deviation is going to shrink, right, as that n increases, because it's on the bottom of our fraction and denominator. All right, so let me show you an example of the central limit theorem in action when we have some heavily skewed data. So we've looked at this before from the book, but this is the Fortune 500, top Fortune 500 companies, the CEO salaries or their compensation in thousands of dollars. So we're talking about 100 million, 200 million, yeah, lots of money. So here, most of those companies, their CEOs make a lower amount of money, but there are some very, very large companies where those are going to be a lot higher. So this is definitely skewed data, right? So our population with sample sizes of 1, this is all 500 of those graphed out, is going to be heavily skewed to the right. And it's not unimodal, it's not symmetric. But what happens is, as we start taking samples, increase sample sizes, like sample 30 of those companies, so here's those 30, and the sample mean compensations, so we take the samples from each one of those 30s, we take the mean from each one of the sample sizes of 30. Notice that this is now becoming less skewed, okay? So as we take sample sizes of 50 companies at a time, so we sample 50, then we sample 50 more with replacement, right? It's even more nearly normal and less skewed. As we increase the sample size to 100, it's becoming much more like a normal model and symmetric and not skewed. And as we take sample sizes of 200, now it looks like it would be appropriate to use a normal model. So the reason why it took such large samples of 200 in this case is because our population was so heavily skewed. When we were looking at the previous example here, this with the dice, I mean, I guess I'll go back to this slide here. When we only had 3 dice with sample size of 3, it still was nearly normal because our original population wasn't heavily skewed. Remember, our original population was unimodal. So what's amazing about statistics is that we can actually, from very small samples, we can have the central limit theorem tells us that the sampling distribution model becomes more nearly normal. And even with small samples, we can do some pretty powerful stuff. All right, so when we have heavily skewed distributions, it still will become, as we increase our sample size, it will still become nearly normal. It just, we needed a much larger sample size of about 200 on this one. So there are a few conditions we need to know for sampling distribution models or inferences with means. So the first, we used to call it the success failure condition. It's just, is our sample size large enough, really? So we used to have to make sure we had at least 10 successes and failures. So if this was our actual population, say a population was where P was, or probability of success was 20%, so we expect 80% failure, 20% success. That's going to be skewed, right? So with sample sizes of 5, notice that the tail is cut off. We're not expecting enough successes in order for this to be it'd be appropriate to use a normal model, right? So we would need to increase the number of trials before we would be guaranteed 3 standard deviations, right? So we would want to expect at least 10 successes and 10 failures, and we could find out how many we would need by taking this value and dividing it by 10 divided by that value, right, which would be basically the inverse of that. I believe, which is 20. I don't know. I put it in the calculator. It's been a while since I've done math. All right, so next one we have here is if we had a sample size of 50, so 20% of 50 is 10. So now we're expecting at least 10. Okay, so that's the value we were looking for, is 50%. So anyway, that's why I did that. So we are expecting at least 10. That guarantees us at least 3 standard deviations, as you can clearly see on this one, in both directions. So everything is good. All right, another example, waist sizes of men. So our population's over here on the side. So where the sample size is 1, that's just going to be our population. This is going to be skewed, not heavily skewed like CEO data, but it is skewed to the right, right? So you get to a certain point where you can't really have a smaller waist, right? It's not really possible for an adult man to have a smaller waist than, I don't know, 26 inches or whatever that value is. But you can always get bigger in a way. So this is going to be skewed to the right. So we're going to have much larger men and more variation on the large end than we would on the smaller end. It kind of gets to a left bound limit there, right? Okay, so if we take sample sizes of 2, so we take 2 men. So of this sample, we say we have 250 men. This is the population of those 250. Now, if we take samples of 2 men and we ask them their waist size, and we take the averages of those 2, and we take a bunch of those samples of 2 pairs of men, then that would give us a sampling distribution that looks something like this. So notice it's still skewed. That's because our proportion was still skewed, and when we do sample sizes of 2, it's not going to have much of the power of the central limit theorem at that point. So increase to the sample size of 5. Now this looks unimodal and symmetric. We can use a bell curve for it now. So that would be a large enough sample. How do you know what's a large enough sample? You just have to I don't know, have experience working with these different populations and knowing how skewed the population is, which will tell you how large the sample size is. So it's not as clean cut as when we were dealing with the success failure condition where we needed 10 successes and 10 failures, but that's okay. You'll get used to it. Sample sizes of 10 and 20, of course, both of those would be perfectly fine at this point because our original population was not that heavily skewed. So here's the central limit theorem, the fundamental theorem of statistics. I'll show it one more time. So our population distribution, it is very skewed in this case. We have our population parameters of our mu and our sigma for our mean and our standard deviation. The sample distributions from those, notice that these sample distributions are going to be skewed as well. They're going to look a lot like the original population. They're just little samples of the population, right? So they're going to have variation from each one. Then if we take the average of those samples, right? So the average waist size or the average height of males or whatever, that's going to give us this sampling distribution. So the sampling distribution becomes more nearly normal as we increase the sample size, right? Even though the original population was skewed. So our sampling distribution model, if we notice here, these, if we take the means of all these and put them together, it's going to look a lot more like a bell curve, which is the central limit theorem, which is awesome. Where the standard deviation is going to be sigma divided by the square root of n, and that's where we get our sampling distribution model. All right, so at this point, you'll look at your assignment. So the lecture was 23 minutes. That wasn't too bad. I'll try to pare it down as much as I can. So look at your assignment. We're going to go through the notes together. These are all on there, just kind of giving you some graphics to go along with it, and then I'll work the example with you. As always, the answers to the odd problems are in the back of the book, so just grade them as you go there. You won't be turning in these assignments. They've asked us not to take grades for the fourth quarter. So it's just honor system, it's on you. So work it out. If you have access to a printer, you're going to want to print these out. That way you can mark on them like we do in class, right? But if you can't, there are other ways you can just write your work on a separate sheet of paper. You also, if you have a tablet, you can, it's a PDF, so there are PDF editors, or you can mark up PDFs. There's different apps. You can look into that. If you have a stylus, that would be pretty easy. Most of you probably prefer just to print it out if you can. If you can't, just do your best and write it down on a separate sheet of paper and go from there. All right, so 25 minutes in. All right, so sampling distribution models for a sample proportion. This summarizes categorical data. So when we have categorical data like success or failure, right, we're dealing with proportions, yes or no. And this is our sampling distribution for the proportions. So if assumptions of independence and random sampling are met, of Of course, it has to be independent. If our samples are not taken independently, like if we're looking at the height of a sample of five people, 5 Americans, right? And we look at families of 5 Americans, and we take samples family at a time. Well, those samples are not going to be they're obviously not independent because those people are all related. They have the same genetics and stuff. So taller family is probably going to be taller in general. Shorter family is probably going to be shorter in general because that's how genetics works. So it's important that when we're sampling, that our samples are independent. So that when we sample, we're sampling people independent of the last person. So they're not related. Otherwise, they'll mess up our stats and it won't work. Also, it has to be a random sample. So we can't claim that our sample is representative of the population if it was not truly a random sample. So if we just did a convenient sample and we only looked at our friends or only seniors or something like that, or if I only looked at my class instead of looking at all the high school, including freshmen, your heights are going to be different, right? You guys are still growing, so that would not be good stats. So with proportions, we have to expect at least 10 successes and 10 failures. That's how we know it's large enough. Then the sampling distribution of proportion is modeled by a normal model with a mean equal to the true proportion value and standard deviation equal to the square root of p times q divided by n. So that's what we did last unit. You guys already know that. So the sampling distribution model for a mean. Now we're summarizing quantitative data. So if we want to know the average for like waist size or height, there are lots of different values. We're now using quantitative data. So we're talking about means in this case instead of proportions. So same thing, same assumptions, basically has to be independent and random samples so that it's a representative sample. The sample size has to be large enough. This is the part that you probably won't like because here we know the 10 successes and failures. That's pretty easy to quantify, right? It's not just up to your feelings or whatever. But in this case, for it to be large enough, it just depends on how skewed the original population is. So with CEO data, we had to have sample size of 200, right? That's because it was so heavily skewed. But if our proportion starts out from a normal distribution, then a very small sample of even an average of 2, like we saw with the dice, I believe, would be probably fine. Or sample sizes of 3 or 4 or 5 would definitely have worked just well with those dice. All right, so the sampling distribution model standard deviation is going to be the sigma, which is the parameter for the actual standard deviation of the population itself, divided by the square root of n. Now, the standard deviation for the binomial model is going to be the square root of p times q times n, and so the p and the q is actually tied into the standard deviation. But now we're talking about different means from different populations. Each one of those is not tied to the value of the proportion like the binomial model was. Now we have to know, is there a large spread in our population, or is it a small spread? So that's why we have to know what the standard deviation from the population is. And it's still going to be decreasing by the square root of n, just like this one was here as well. So very similar to what we've been doing. Fundamental theorem of statistics. So central limit theorem, this one's important. So the sampling distribution model of a sample mean and proportion from a random sample is approximately normal for a large sample size of n, regardless of the shape of the original population distribution of the population, whether it's skewed, binomial, unimodal as well, or anything, or multimodal. Then as long as the observations are independent. So looking here, our population was skewed, our sample distributions are still skewed, but when we take the averages of those sample distributions, that becomes more nearly normal as our sample size increases. So as long as it's a large enough sample, we can use a sampling distribution model, which is nice. So our conditions, again, has to be random. So if they're not randomly in experiments, they have to be randomly assigned. Observational studies and surveys have to have randomly selected participants. Otherwise, in experiments, you have lurking variables and confounding that can happen. In observational studies and surveys, it's not a representative sample if it's not a random sample. So all of our data gathering techniques, those still hold, and they're important. Independence assumptions. So 10% condition, it's not going to be possible for us to know that they're sampled independently. So what we need to do is use the 10% condition to override it, because most of the time we're sampling without replacement. And so it's not actually truly going to be independent. It's like drawing an ace out of a deck of cards. Unless you replace that ace, you know that the probability of an ace being drawn again is going to go down, right? So as long as we're sampling less than 10% of the overall population, we can override the independence assumption, because it will change the probabilities, but it's so small of a change that it doesn't actually matter. So we're still overriding that with a 10% condition, just like we did before. Large enough sample, we used to call this a success failure condition for proportions, but now for means, it just depends on what your population is. So you need to kind of be able to estimate how skewed or how unimodal and symmetric our original population is going to be. And the more skewed it is, like CEO data, the larger the sample size has to be. Think like 200. If the population is nearly normal, we can use much smaller sample sizes like 5 or maybe even 3, which would have worked just fine with the dice. So let me do an example. This is number 40 from the book, Home Values. So assessment records indicate that values of homes in a small city is skewed to the right, with a mean of $140,000 and a standard deviation of $60,000. To check the accuracy of the assessment data, an official plans to conduct a detailed appraisal of 100 homes. So that's going to be our sample size right there. So 100 homes selected at random. So it is selected at random, which is important. That means that it would be representative. Are they independent? Well, let's go through our conditions real quick. So randomization condition. So should we expect the samples to be representative? Well, yes, it tells us that it's a random sample. So it should be representative. That's fine. 10% condition. So it's not truly going to be independent, because we're probably sampling without replacement. We wouldn't select the same house to appraise twice. They just don't do that. So as long as we're sampling less than 10% of the population of all the homes, then we're good. Well, he's selecting 100. So do we expect there to be more than 1,000 homes in the small city? Well, yes. If it was a town, like a small town, they probably don't have 1,000 homes. But in a small city, they should have at least 1,000 homes. So we're fine. We can override that with the sampling without replacement, because it's not actually independent, with the fact that we're sampling less than 10%, so it doesn't change that much. Large enough sample. Well, how do we expect the original proportion to look? So they're saying the average home in this small city is about 140,000. At least that's what we expect it to be. Now, there's going to be a point where you can only get so small of a house. So the houses are only going to be so cheap, right? So maybe you could get a $50,000 house. But the population is definitely going to be skewed to the right, because you can always have a more expensive house, right? So if Russell Westbrook lived there, I mean, his multi-million-dollar house is going to skew the data, right? So or anyone, right? So yeah, that's going to now be skewed to the right. But how far is it skewed to the right? Well, probably pretty greatly. $1 million house is going to be many standard deviations above that. So the question is this a large enough sample to take into account how skewed our population is? Well, yes, I think so. So a sample size of 100 is very large. It's not going to be as skewed as the CEO data, the CEO salaries we talked about. So I think 100 should be large enough even to make the sampling distribution model nearly normal, even though our population is skewed. So a sample size of 100 should be large enough to make the sampling distribution more nearly normal by central limit theorem. Okay, exactly what I just said. All right, so the next part B, using our empirical rule, draw and label the appropriate sampling distribution model for the mean and values of the homes. So our sampling distribution model is going to be centered at the population's mean as well. So that's going to be 140,000. So it's going to be centered at 140,000. The next question we have is, how far apart is one standard deviation? So that's going to come from our new formula. So the standard deviation, the sigma of our population, we're assuming that that's 60,000. So it's going to be 60,000 divided by the square root of n. Well, square root of n is 100. Let's see if I can write this stuff out here for you. So this is equal to, I'm afraid that my computer is going to be very laggy, but it's actually working out just fine. So 60,000 divided by the square root of 100. So the square root of 100 is just 10, right? So this is easy. When we divide by 10, we just remove one of the zeros. So this is going to be a standard deviation for a sampling distribution model of 6,000. So centered at 140K, then we have 146,000, 152 is 2 standard deviations above, and the same thing going to the bottom. So that's how we would find that. So from this, the next question is, you can already see, is like, if he had a mean of those, the 100 homes that he sampled, and their average was, let's say, 150,000, would that be considered unusual? Well, looking at our sampling distribution model, 150,000 here, somewhere about there, is within 2 standard deviations. So it's not necessarily considered to be an unusual sample. That could have just occurred by sampling variation. But let's say he had something beyond 2 standard deviation. Let's say that he had an average of, let's say, about 160,000. Now, that could have happened if he got a very large, like if he, in his sample, he had he had the $1 million house, right? That could have happened, and that could skew our mean. But with our sample size of 100, that would be probably pretty unusual. So again, we could still then go into our hypothesis testing with the null hypothesis and the alternative. And we could have a false positive because we ended up sampling that one multi-million-dollar house or something like that in a small city. But overall, that's pretty much how all this stuff works. So we'll get into all the other stuff more in more detail later, but I think that's pretty much all I have for you for today. Yep, that's it. So do your assignments, and we'll finish up this chapter tomorrow. So I'll see you then.